Welcome all for coming. My name is Denneman. I am the Chief Evangelist of PernixData. Prior to working for PernixData, I worked at VMware in the DRS and vMotion team, and I did some architectures for them as well. And prior to that, I was a independent architect working on a lot of architectures within Europe. So let me put this on. So this is actually one of my first architectures I've done. And prior to working with virtualization, I was an Exchange architect, and I built a 30,000 mailbox environment in 2004. And in 2005, somebody showed me vMotion, and from that point on, I was hooked, and I really wanted to marry those two technologies together. So I thought this is an excellent way of getting Exchange, getting it decoupled from hardware. So we bought some ESX host, we got some funding for an array, and because of the price of the array, we had to allow other workloads on that array, primarily databases. So in the beginning, when we started to virtualize the Exchange environment, it went pretty well, and the performance was pretty good. Now, one of the problems was we were really successful in deploying new virtual machines, and the organization got wind of that. Meaning that we could power on a system within a week, rack stacked, or not even rack stacked, but completely operational within a week. The physical team took 3 months to do it. So everybody thought, I don't need the performance, I'd rather go for a virtual machine. That was back in 2005, right? So we got a lot of bad performance really soon. So what we did was we started to scale out on the compute level. Well, it took us 4 months because we had to wait for those machines as well, of course. Now, from that point on, it performed again a little bit, but really soon we had the same problem again. Now, the database guys, they were really progressive as well, so they thought, let's virtualize databases as well. So we had a lot of uncontrolled I/O going towards the storage system. So we looked at it and we thought, okay, compute is not a problem anymore. What is the bottleneck? And we thought bandwidth between the ESX host and the array is the bottleneck. So we added more bandwidth. It did not solve the problem. Then we added new SAN directors, basically providing more compute power in the storage area network. It did not basically provide the performance boost we wanted. So the last step was more spindles. That worked for a couple of months before we got into the same problem again. Now, at one point, we couldn't add more spindles to the array because the array has a closed form factor. So we bought a new array. The problem was when the lorry driver tried to unload the array, he was very careful with getting that thing off the truck because he thought it would break the backside of his truck. So we looked at it and we thought, hey, if he's already scared about the weight, how about our data center? Because we used a floating data center floor. So we had to actually calculate the pounds, the pressure per square inch, and we figured out that the moment we put it on our data center floor, it will drop 2 floors immediately. So, big problem. So we actually had a welder come in with H-beams and created the construction to put it on. That took us, again, 3 months. Now, this happened for me in 2005, but in reality, from 2005 onwards, we had the same problems over and over again, right? You see workload pouring on into an infrastructure up to the point where it breaks down or when the performance slows down, add more spindles, and then rinse and repeat. So the industry looked at it and thought, let's do it differently. And what they came up with was Flash. And I believe that Flash is our savior of the virtualized data center. It's small, it's light, it provides an incredible amount of performance and an extreme amount of low latency, right? But where do you put Flash? So you can put it in the server, you can put it in the array, but you can also put it in the network. I've seen 2 devices that actually provided Flash in the network. There was a QLogic one and there was a Fusion IO one. The Fusion IO one was actually in Utah, which happened to be the location of the headquarters of Fusion IO. So maybe that was the explanation why I saw it only there. So in reality, it's either server or it's array. Now, if you look at the true essence of a flash device, it's all about performance, getting the best out of that device. So it becomes a matter of location. Where do you want to put that flash device? And in my take, you want to put the producer really close to the consumer, right, to get the best out of it. So, and then there's the whole architecture. Looking at a hypervisor itself, that thing has context-rich information, meaning that when a virtual machine issues an I/O, it knows that that I/O comes from that virtual machine. Now, you know, and Joe talked about kittens and chickens a while ago, I think last year here. The thing is, you know exactly which application is running on which virtual machine of most of the time. So you know what application you want to prioritize. But the problem is, the moment that I/O leaves that hypervisor, that I/O will get the last identification number. That's typically the WWN from the HBA or the address of the Ethernet card. Meaning that every I/O, regardless of where it comes from virtual machines, from business applications, becomes anonymous. Now, how do you deal with that from a quality of service, right? How do you ensure that a particular virtual machine will get the performance it needs because it's that valuable for your organization, right? So that's a really difficult trick to do. Another thing, of course, is the amount of travel an I/O needs to do. Like I said, you want to put a flash device as close to the application as possible. The moment you're going to put a flash device in an array, you're going to basically put it away for from a long distance perspective, and I'll come to that a little bit later. So let's track the journey of an I/O, right? Let's see what happens with an I/O. So you start off sending out an I/O. The moment it hits the network, it becomes anonymous. Now, anonymity is not always a good thing, right? Because you have queues everywhere in your environment. And queues mean latency, because every single thing you put between the application and the device itself will show up as latency, right? Queues, algorithms, priority stacks, whatever, right? So this is a diagram that Chad Sackett, the VP of EMC, made, indicating the amount of queues and IOCs from an iSCSI stack performance. And every queue will mean some sort of latency, some sort of prioritization, right? How do you deal with that from an anonymous perspective? So you're going to put your flash in there. I don't think that's the best use case for flash, because you start to penalize flash itself, right? So look what the industry is doing right now. They're saying light speed is not fast enough. We need to do something different here. Because in reality, flash behind an HBA, you're actually talking to that device on light speed, and yet it's still not fast enough. So what the industry is doing is it's moving flash on the PCIe, in the server itself. Not even that, we're talking about flash in memory slots, or even memory to accelerate data, right? So compare that to the whole movement we're doing in our architecture, right? So why don't we do something good for the software-defined data center, right? Why don't we take this opportunity not just to create cheaper storage systems and create catch-all LUNs and data store, but think about this from an application-centric perspective, when you can use policy-based management to actually provide the performance your application needs, right? So how do you do that? Well, we do that with PernixData FEP. And what will it provide you? Because you're putting flash in the server, you're going to get high IOPS. You're going to leverage those IOPS straight away, because you're removing a lot of moving parts between the flash device and the application itself. So your application performance can spike, while the data store writes remain the same. It will provide you consistency, low latency because you're removing a lot of moving parts, right? Because you're talking to that device straight away, you don't have to wait on all those queues. So again, it doesn't matter if you have a lousy data store performance, you're getting your application performance from your flash device. And another thing, and I think this is actually the most brilliant part of it, because you're going to absorb a lot of IOs in the server itself, you're going to offload the entire infrastructure from that load, meaning that not accelerated virtual machines, not accelerated applications, even physical machines hitting that same array will get a better performance because you're offloading the workload on your infrastructure, giving more air to the non-accelerated applications. So what are you doing is you're still using your normal infrastructure. You still use a storage array. But from this point on, you're going to use that array for your data services and capacity only. Performance is something that you will bring to your compute layer. So turning your compute layer into a performance layer. That will provide you the best scale-out possibilities, right? Because the moment you need to run more virtual machines, you need more performance on CPU, on memory, and on storage. Well, by putting it inside the ESX host itself, you're coupling them together, and you can scale out accordingly. So how does it look like? So you bring your ESX host, your own ESX host to the party, your own storage array to the party, and the first thing you do is you're going to buy some flash devices. Use the HCL to make sure that the flash device, primarily on PCIe, is supported by VMware. The reason why I say that is because we live inside the hypervisor. We created an extension model, so we extend the hypervisor with our code. We all come from a VMware background. Our CTO has invented VMFS, VAI, pluggable storage architecture, vVols, and something else, and a lot of other things, but those are the most things you are actually using in your data center right now, or vVols maybe next year, right? So we know exactly how to extend the kernel in such a way that is lightweight, provides the least amount of overhead, and still be supported by VMware. We are supported by VMware, meaning that when you install that extension model, you can use the vSphere Update Manager because it's signed by VMware. And the beauty of it is, if you have a problem in your environment, maybe you have a network problem and you call up VMware, they're not going to ask you, hey, deinstall FTP first, kill your performance first because we're having a network problem. No, it's supported by VMware, right? So what you do is you put your ESX host into maintenance mode, you're going to install the VIP, you're going to exit the host out of maintenance mode, and from that point on, your host is Pernixed, right? From that point on, you can start to accelerate your virtual machines. Now, not exactly, because you need to run the PernixData management server. That's a Windows-based appliance using a database. Typically, what we see is that customers are installing that alongside the vCenter server. Now, that thing is not a part of the I/O stack itself, meaning that if that thing fails, there's no impact on the service of the virtual machine itself. Primarily what it does, it feeds the vSphere client, or it feeds the web UI with the tools for FTP. So what you see when you open up vSphere client is you see an integrated part, feeling that it was always there all along. Now when you have that PernixData management server installed and you have those tabs inside your vSphere client or the integrated parts in the web UI, you can create a FTP cluster. From that point on, you can start accelerate virtual machines. Now the beauty of it is, you can do that on the fly. You don't have to reboot anything. So you don't have to install anything inside the virtual machine. You don't have to install a host-based agent. You don't have to install a driver. You don't even have to move the virtual machine to another data store. You just accelerate it, and it automatically becomes faster without interrupting the service. Same thing with the ESX host. Just put it in maintenance mode, get it out of maintenance mode, you're done. You don't have to reboot it. Storage array, exactly the same. Just leave it because we're still using it for the capacity layer, right? So because we're creating an FTP cluster, we align to the vSphere cluster, meaning that we support all the vSphere cluster services. So when you accelerate a virtual machine, you're going to create data footprint on the local flash device. But what happens if DRS moves the virtual machine from one host to another host, right? From that point on, that virtual machine will be treated with an empty flash device. Well, for a performance perspective, that's a bad thing, right? Well, FTP has what we call a cache coherency protocol, meaning that we know exactly where each bit of data is. Meaning that if the virtual machine is reading data that we have stored on another flash device in another host in the vSphere cluster, we're going to just grab that piece of data, bring it over to the local flash device, and service it up from that device, right? So the next time that virtual machine will read that data again, and I will assure you it will, you will see it coming from your local flash device again. This allows us to move in scale. This allows customers of ours to accelerate more than 1,000 virtual machines because we're not pulling all the stale data over the network. We use the Ethernet network for this. By default, we use the vMotion network, but you can use any other VM kernel network to your liking. So you can create your own FTP distributed layer, if you like. Now, let's take a step back and see what type of steps is needed to actually accelerate a virtual machine. So when you select your vSphere cluster, you create your FTP cluster, give it a name, add some flash devices to that cluster. That's on a logical basis, not on a physical basis, and then select your virtual machine. Now, I talked to a lot of customers, and I asked, okay, so how do you like this model? Is it good? What's difficult? And they actually pointed out that providing a cool name to the FTP cluster was one of the most difficult things to do. So I think that's a good thing, right? So the last part, select the virtual machine. What happens there? Well, you go inside the vSphere client, you go to your FTP tab inside your vSphere cluster. You're going to select that virtual machine, and you're going to select the write policy. In this case, I use write back. Now, the next thing I need to do is provide the amount of writes that are committed to other components as well, and I'll come to that later. When I select that and I click on done, from that point on, that virtual machine is accelerated. From that point on, we use the local flash device to accelerate your data. Now, that involves a few clicks, and like I said, if you have more than 1,000 virtual machines that you want to accelerate, you don't want to do this every single time. So you can use PowerShell, or what you also can do is you can create a default policy per data store, meaning that every virtual machine that's on that data store will automatically get that policy attached to it. That means that every existing virtual machine will be accelerated at that particular time. But not only that, new virtual machines that come in, either by provisioning or by storage vMotion, will get attached that new write policy. If you have a particular virtual machine that needs to have a different policy, you can override it on a per VM basis, right? So think about this from a policy management. Think about how to use this with storage policies, right? We support it as well. So you can start to integrate it in your normal operational processes. If you don't use VM storage policies, great, because this doesn't change anything from your operational perspective. Because you still need to select the compute layer, cluster, you still need to select the data store or data store cluster. Well, that's exactly the same. But now, from that point on, it's accelerated automatically. So I talked a little bit about write back. We have two write policies, write through and write back. And the main difference between those two is basically the timing of the write of the data to the data store. Because we're not a data store. We're not a persistent layer. We still have to write that data out. But the timing is the crucial difference. When you select write through, what we do when we see an I/O come in, a write I/O, we will send the data in parallel to the local flash device and to the data store. The moment both resources acknowledge that they written the data, it will be the completion will be sent to the virtual machine again, right? So the effective path from the virtual machine to the data store is exactly the same. So your write latency is partially untouched. The reason why I say partially untouched is because when the virtual machine reads that data after the write, this typically happens a lot, it's called read after write, you see that those reads will be serviced from the flash device. Those reads will be absorbed in that layer, meaning that those reads, those IOs will not hit the data store. The array doesn't need to look up that data because we don't even send it to the array. meaning that you're going to reduce a lot of load on your storage area network, on your storage array, on your storage controller, allowing the writes to use that bandwidth to actually get better performance. So you provide more air. But if you want to have the best performance, there's write back. And with write back, we're going to send the data to the local flash device, and once we write it to the local flash device, we're going to acknowledge it straight up. You get the best I/O, you get the enormous amounts of I/Os, and you get the lowest latency, right? Because we're removing a lot of moving parts here. Now, because we're not a data store, we still need to write it to the data store. So that means that we can do that in different ways, because the application already received the acknowledgement, meaning he thinks it's already there. So everything becomes transparent from that point on. Now, one of the things is, if that data is stuck inside the ESX host, what will happen if the ESX host fails or the flash device fails, right? You're going to have a problem. Well, because of that, we build a fault tolerance in our layer, so in the software layer. So when the virtual machine writes data, it will write data to other flash devices in the cluster, and that was basically what I was alluding to in that screenshot. So when you select write back and you select one pair, we will send the data to the local flash device and to the remote flash device. If both resources acknowledge, we will complete the I/O. We use the Ethernet network for that as well. And because an Ethernet network is a point-to-point connection, knowing exactly when to enter and when to exit, it's extremely fast. It's not shared again. So you get the benefits from that as well. So the moment that flash device fails, the local flash device fails, or the ESX host fails, that peer host will detect that there's a failure in the environment, and he will send out the pending writes to the data store. He will do that in such a manner that if HA will restart that virtual machine, he will say to HA, stop, I'm still writing data, and until the data is all on the data store, it will basically loosen up the lock, and HA can restart that virtual machine again. So the virtual machine starts with all the data on the data store. Now, typically, that's a really small amount of data on the peer host, because the flash device, the local host, will will basically send out that I/O as fast as possible. Now, in Joe's keynote, he talked about high availability, and at one point talking about the software components being high available. Sorry. So here's the thing, right? So think about fault domains in general. Who in the room are using blade structures, blade centers? Cool. Are you treating that as a failure domain, as a fault domain? Meaning that, are you spanning your vSphere clusters across the blade centers? Yeah? Okay. So what happens if you use write back and you select you select one host to have the redundant writes? What happens if FEP selects a host inside their own blade structure, and that blade structure goes down, the mid plane goes down? You have all that data stuck inside your blade center. So because of that, we use fault domains. So now you can say, I want to store my pending writes, my replica data, into another fault domain. So if my entire fault domain goes down, I can send it out via another fault domain. Now, when we talk about software failure, what happens if FEP fails for whatever reason, right? We exactly know that as well, and we're going to send out those writes again. Now, a favorite example, and I don't want to bash HP, but I think most of you who used HP have once endured the HP SIM drama of installing something that tries to guarantee uptime, and by doing so, you create a PSOD. What happens if you select two ESX hosts as peers, right? The moment we see a host disappear, the other peer host will send out the data. Now, we've seen this with a customer. When the source host was HP SIM installed on, it went down, a purple screen of death. The second peer host start to write out the pending writes to the data. But one of the administrators was also trying to install HPSIM on that one as well. So that thing went down as well, only covering 30% of the pending writes. Now the third host figured that one out, that hey, the source host is gone, the peer host is gone. I need to send out those pending writes. He started to write out those data where the peer host left off. Now, bad stroke of luck. They installed HPSIM on that thing as well. So he was done 40% of that remaining part. So that thing went down. The first host was up again. He detected where the second peer host left off, and he completed the amount of IOs. Well, this is basically how FEP fault tolerance work. We know exactly where the data is, what data is located where, and if it's already written to the data store. And they will take care of themselves, no matter if it's a software failure or if it's a hardware failure, right? So because of we're using fault tolerance, and we can now start to stretch data over time, we can now decide what to do with the data. You can start to think about restructuring data flows, right? So one of the things, like I said, the moment you start to absorb a lot of IOs in your environment, you're going to see benefits. What we do in the UI is we're going to track what we like to call hero numbers, meaning that we're going to show you how many reads we service from the flash device, how many terabytes of data we're not sending over the storage area network, and how many writes see a significantly low latency. Now the thing is, those 8 billion reads happened in 6 weeks. It was a Dutch customer. They accelerated 50 SQL servers. 8 billion reads did not traverse the network. 318 terabytes of data did not hit the storage area network, did not hit the storage controller, meaning that the writes, they saw an extreme benefit, not only from a flash perspective, but also when we are going to send it out to the data store as well. Not only that, the applications that were accelerated saw a benefit from it as well. So what you see with local resources is you give the application to spike. And one of the things we saw, and one of the things I always try to, when I was called into an environment to troubleshoot, we saw a lot of forced cache flushes on the storage controller end, meaning that when an application spiked, it didn't fill up the entire cache of the storage controller, but it did it to a certain part. Now the rest of the virtual machines start to hit that storage controller as well, filling up to the threshold, and basically saying to the storage controller saying, everybody back off, I need to commit those writes to my storage to my backend because I want to ensure that the data is really safe. That being said, that's actually a denial of service to your entire environment, right? Well, by using server-side media like Flash, you can start to spike over and over and over again. Because we have fault tolerance, we can now start to think about, hey, can we not send out those writes in a more uniform manner? So what we do is we model the storage array. We know exactly what the storage array is capable of, and we're going to send out the IOs that the array likes, trying to avoid those forced cache flushes, right? The data store writes are completely transparent, so it doesn't even matter for the application. So talking about storage controllers, I walked around VMworld and I asked a lot of storage vendors, what is your storage controller responsibility? And this is basically the list what it needs to do on a daily basis. Now, I'm not going to read it up because you can read faster than I can talk. But in reality, it's a lot of things, right? That those two machines, because they're just two servers, need to cope with. What we saw with a lot of customers, what they were actually saturating their storage controllers. Their storage vendor said you can even add more capacity because you're already saturating your storage controllers. If one storage controller fails over, you're going to have a bad time. Meaning that the amount of IOs they're sending to, the amount of services they're doing on that level, basically robbing them from doing a capacity scale out, right? So by reducing the amount of IO, you're going to reduce the amount of CPU utilization on your storage controller as well, allowing you to actually start to scale out at capacity. Scale out on performance is something you do at hour level, right? So this is a screenshot from a customer, and they didn't have a good relationship with their storage group. So they asked, can you give me a screenshot of the last 4 weeks of the storage group? And in the third week, they actually enabled PernixData. And that moment on, it actually triggered complete frenzy at the storage team. Because what happened, they couldn't figure out where the load was. So they started to troubleshoot for 2 days the entire environment. They didn't call up the virtualization team because, well, they didn't have a good relationship. After 2 days, they gave up. They asked them, how many virtual machines did you power down? Because we see an extreme reduction in load. Well, we didn't. We just started to provide performance in a different way. Now, the thing is that right part of the performance graph is actually the most important thing for a storage admin. Because from that point on, that's the load he's coping with. From that point on, he can think about, how can I start to architect my storage environment that I still can provide that load while still giving the best capacity? So what we see typically after a couple of weeks accelerating workload, we see storage groups start to initialize different architectures within their storage environments, going from array 10 to a more economic way to provide more capacity, right? They don't have to provide that peak load anymore. This also provides a way to extend the life cycle of the array itself. And when that thing is really out of its life cycle, you can then think about getting a smaller array because you don't have to worry about that load anymore, right? We had one customer who had a big fat VMUG on their primary environment, and they were trying to build a test and development environment with a smaller VNXE. They installed FEP on it, and within 4 weeks they had to shut it down because the test and dev environment was faster than the VMUG, giving them a worse performance perspective for the application. So yeah, there are some challenges with that, right? If you want to really integrate it in your environment. So here's the thing. On the left side, we have the virtual machine in an unaccelerated mode, meaning that the array provides storage performance, capacity, and data services. On the right side, it's being accelerated. And what you see is that the VM observed latency overlays the datastore performance, meaning that the datastore provides the performance. On the fly, we start to accelerate it. So from the point of acceleration, you see the VM observed latency hitting the flash device. Now this is just a couple of minutes, but the longer you start to run on flash, the more stable it gets because you start to get more data in. Now the most interesting part was that part, the datastore latency. Because from that point on, the datastore latency was reduced because we absorbed a lot of load on that datastore. This means that not only did we basically solved a pain point from a performance perspective from that application, but we also increased the performance of all the other virtual machines running on that same data store because it saw less load. So now you can think about scaling out your performance architecture, right? And like I said, the moment you have new virtual machines in your environment, you're going to add another host. Because you use server-side media, you're going to scale out accordingly. Now the thing is, today you can buy a flash device that provides 50,000 IOs, right? Maybe next year 100,000 IOs. Maybe in 2 years down the line, the industry provides you 250,000 IOs. Well, the fun thing is, because of that, the moment you need more compute power, you can use the latest and greatest technology at your disposal. So compare that to something called an all-flash array or whatever. You can buy an array right now, you have to pay a lot of money to get it, and yeah, it sure looks sexy right now, but does it look sexy in 3 years down the line, right? It's still the same box, right? With this, you can get the latest and greatest technology. Now, I created this slide a couple of months ago, and I thought, well, maybe it's reasonable to expect 250,000 IOs in 2 years, maybe 3 years. Well, actually, no. Actually, it's already here right now, because Intel provides you with the P3700. It's a SSD on a PCIe device. You get 250,000 IOs, real IOs, so 70/30 4K mix for $1,200 list price. That's 250,000 IOs coming from one small device. 4 hosts, you have 1 million IOs, right? So what do you do actually with 1 million IOs, right? in reality, it's all about changing the perception of storage performance. So from this point on, with this latency and with these amount of IOs, storage performance is not the bottleneck anymore. You are absolutely sure that you can provide that performance, right? Meaning that you can now think about different application landscape, try to solve it in a different way, right? And that's really, really powerful. So one of the things that the industry is looking at, and I alluded to in one of the previous slides, is we're going from flash inside memory slots to actually memory. And you see that Intel is supporting 1.5 terabytes per CPU. So think about a four-way host providing you 6 terabytes of memory. What can you do with 6 terabytes of memory? vSphere 5.5 Update 2 supports 6 terabytes of memory. vSphere 6 is going to support at least 6 terabytes of memory. What do you do with all that memory? Are you going to provide it to your virtual machines as system memory? Or are you going to use it in FEP? Because from this point on, in FEP 2.0, we can actually use memory as a fault tolerance acceleration media. Because we use fault tolerance, because we store data on separate locations, because we provide you full domains, you can now ensure that the data is safe in your environment, right? Now the thing is, when you look at a software stack, I still have some minutes, you're now thinking about removing those levels of moving parts as well. Because the moment an I.O. comes in from the CPU, it goes to memory, and then it goes to the software layer going towards the SCSI layer, and then it will actually end up as a particular block hitting a flash device that has a preferred block size. If you create larger blocks, you're going to need to split it up. All these things are basically impacting latency. With memory, you don't have that because there's not a preferred block size in memory. It's just a big pool of resources. Meaning that from that point on, your block size doesn't even actually, you don't even care about block sizes anymore from a perspective. So what you always hear, I can give you a million IOs, right? Yeah, but the next question is always, at what block size, right? With memory, it doesn't care anymore because you're not dealing with those software structures anymore. We will take care of that at a different layer, again, transparent, right? Are we the first one that uses memory? No, we're not. So the industry started out with changing applications. Memcached is a good example, Gemfire is a good example. Problem is, you almost need a PhD degree to actually figure that one out and include it in your application. The ISVs, such as Oracle and Microsoft, thought, let's do the heavy lifting for our customers and incorporate memory acceleration inside our environment. SAP HANA is a good example, Oracle 12c is an example, right? But even with SAP HANA, you still need to provide ACID. So you still need to provide the integrity of the data itself, typically using a flash device locally to store that, meaning that you're going to impact your service level again because there's no mobility, right? In our case, we provide you distributed fault-tolerant memory. And I think it's the same thing as HA, right? Where before HA, you had to use either something in the application itself or a Microsoft cluster or Veritas cluster to provide high availability. HA came along, VMware came along with HA, just saying, well, just add a tick box and select a couple of policies in your vSphere cluster. And from that point on, every virtual machine is protected by HA. Same thing here, not protection, it's acceleration, right? Because you install it at the cluster layer, from that point on, you can actually accelerate every virtual machine using memory as an acceleration tool, right? So to conclude, we're providing you server-side storage intelligence. We're abstracting all the performance layers, and we're giving you a way to scale out. That's on a short-term basis, right? On a long-term basis, you can think about changing your entire structure to more policy-driven. You decide which application to accelerate. You decide which application to get the best benefit, offloading those noisy neighbors to the rest of your environment, basically giving you better performance all over. So I will leave you with this thought, right? Instead of using flash inside a storage system, creating faster and cheaper storage systems, using that 10,000x improvement just to create a faster storage array is not the way to go. Look at what we did in back of the 2000s, right? When the CPU had a speed increase from 200 megahertz to 2 gigahertz. What did we do with it? Yeah, we got better performance from particular applications, but some brilliant minds thought, let's consolidate. Let's use those resources and start virtualization on an x86 platform. That was only on a 10x improvement. What are we doing now with a 10,000 improvement? Just sticking it in the same way? I think we need to do something different. Software-defined data center is here to stay. Think about using all new gen server media to actually create that, to make that vision a reality. Well, I thank you all for coming this early morning. Yeah.